Today we're going to begin talking about probability, and today is the easier of the 2 days. We're going to hit one today, one tomorrow. Today is somewhat straightforward. There's a little bit of trickery to it towards the end, but as we know from probably 4th and 5th grade when we first were exposed to probability, the probability of an event happening is the number of favorable outcomes over the number of total outcomes. Single event probability is just when one thing happens and there's only one outcome. Compound probability, multiple outcomes for multiple events. So this is an example of a single event probability where we have 5 pencils, 4 pens in a bag, and we want the probability of reaching in and drawing out a pen. So one thing happening, one outcome. So we have a total of 4 pens over 9 total things we could pick from. And I would prefer you leave all these in exact value or in fraction form. Some books, some publishers will put it in decimals and round things off, but I would prefer the fractions when we can. Sometimes you won't be able to use fractions, but let's just do it that way for now. A mutually exclusive event, or events if you will, are when you have a compound probability, 2 things possibly happening, but it's impossible for both of them to happen at the same time. So they act like 2 single and removed events. So typically we will see a mutually exclusive event type problem when it says the probability of one thing or another thing happening, and in that case, if they're exclusive, we take and add their 2 probabilities up. So let's take a look at an example like this. I've got a deck of cards laid out here for those of you who don't play cards. With the deck of cards, there's 4 different suits. There are numbers 2 through 10, and 4 of each of those type of numbers, 1 in each suit. There are 4 aces, 1 of each suit. There are a total of 12 face cards, Jack, Queen, and King, where once again we have 1 of each suit, and notice there are 2 different colors. So we want to find the probability of drawing an ace or a 10. Probability of drawing an ace is 4 out of a total of, there's 52 cards in a deck. Probability of drawing a 10 is another 4 out of 52. Since neither one of these can be the same draw, we'd have a total of 8 over 52, or 2/13. Now, another type of probability is where we have inclusive events, which are not mutually exclusive. And these events can happen the same time where there's some kind of an overlap. So the probability that A or B equals the probability of A plus the probability of B, but we've doubled up since something's an overlap, so you have to subtract it out. So probability of A plus the probability of B minus the probability of A and B happening at the same time. Let's do a similar example. Here's our deck of cards again. We want the probability of drawing a red card. Well, half of the cards are red, and in 52 there's 26 of those. So that's the red part. Probability of drawing a king, here are the kings, is 4 out of 52. But within the reds, if you look here, we've already chosen kings. And now we're asked to choose them again. So there's an overlap of 2 in those 2 options. So we have to subtract that out. So we end up with a total of 28 over 52. 4 goes into both of those, 7 here, 13 times here. So sometimes we don't necessarily have a picture. This wouldn't be here in the original problem. I just drew this in to get us started. So we have a total of 900 pints of ice cream available for sale. 200 are sugarless, 500 are vanilla, and 50 are sugarless and vanilla. And we want to know the probability that a pint selected at random is either sugarless or vanilla. This is called a Venn diagram. And sometimes I use these when I have non-mutually exclusive events. Don't have to, but sometimes it helps. So I know I've got a total of 50 that are both sugarless and vanilla. So I usually put this in here where my overlap is to remind me that that's got to be taken out. Then I have a total of 500 vanilla, but in this vanilla circle right here, I've already got 50. So there must be 450 remaining. And then I have a total of 200 in the sugarless, but I have 50 already, so there's 150 here. The reason why this helps is it tells us how much has been used so far, because at this point I only have a total of 200 and 450, or 650 total, which means that in our whole sample space, if I were to extend this, there is other ice cream that's neither sugarless nor vanilla, and I've got 250 here. So if my probability asked, well, how many are only sugarless, then I could answer this with 150 out of 900, because this is only sugarless, not sugarless and vanilla. Okay? And then if they ask me how many are neither sugarless or vanilla, I can answer with this, because those are the others. But in this problem I can say, well, I know I've got 200 sugarless over 900 total. I've got 500 vanilla over 900 total, but I've got this overlap of 50 that I have to take out. And then we just grind that out together, and after reducing we get 13 over 18. So let's do a couple other examples. We've got 3 green, 7 red, 5 white. We want to know the probability of choosing red or white. Alright. This is exclusive because if I pick a red can't be a green and a red can't be a white. So we're going to add these two probabilities up. I have 7 over 15. And then the white is 5 over 15. Giving me 12 over 15, which is going to reduce to 4/5. In this case, write the numbers 1 through 10 on a card, place them in a bag. Probability of drawing an even or a 9. Seems like there's going to be some overlap here, so I have my numbers written over here. Let's do this problem. If I want an even number, 1, 2, 3, 4, that's 5 out of 10. It's for my even. And then I need a 9. Doesn't look like there's any overlap. That's 1 out of 10. So I have a total of 6/10, or in this case 3/5. Next one, I want the probability of a multiple of 3 or a number greater than 5. Well, multiples of 3 are 3, 6, and 9. So the multiples of 3, I've got 3/10. Then I want a number greater than 5. If I want a number greater than 5, 6 is greater than 5, 7 is greater than 5, 8, 9, and 10. So you'll see there's 1, 2, 3, 4, 5 numbers in yellow. But I've got overlap. And overlap is 2/5, or 2/10, sorry. So I add these up, get 6/10, which again equals 3/5. Lastly, you got a grocery store, and 25% of the people use coupons, 43% bring their own bags, and 12% do both. And we want the probability of customers who do neither. So these are actually kind of probabilities or fractions, and your entire probability for anything to happen is 100%. So these are parts of those 100. Assume there's 100 people. So let's draw a couple circles out to maybe help us out in this case. All right, and here's one and another. Let's clean that up a little bit. Bring this guy down here. So we're going to talk coupons, we're going to talk bags, and this is going to be C and B. And then everything else outside of that is going to be a neither case. So let's draw a rectangle outside. And outside we'll have neither. So I know I have 25 use coupons, 43 that bring their own bags, and 12 that do both. So I'm going to put my 12 right here. And if I have 25 with coupons, then since I already have 12, I've got 13 here. 43 bring their own bags, but since I already have 12 in the bag circle, I just subtract from 43. That gives me 31. So a total of 43 in there. Now, I want to know how many do neither. I should have 100 total percent. So what I have now is I have 43, 46, 56 total. So if I'm looking for 100 and I have 56, I have 44 left. So out here is 44% of the people. They do neither. And we want to find that probability. That's 44 over 100, or 44%. That's all we've got for today. No Connect Ed, and we'll discuss this tomorrow.